Alright, the continuation of 4.1. We need to talk about zeros, multiplicity, and behavior of polynomial functions, so let's start by looking at zeros. A zero refers to x values that would result in a zero when substituted in the function. Graphically, that means the function either crossed or touched the x-axis. We've seen this with a lot of polynomial functions, whether they're quadratics or cubics or whatever else we've looked at. So, for example, that's a zero because it crossed. But if the line just goes like this and touches, then that would be considered a zero as well. So both of these are considered a zero. This has some consequences for other definitions and words that we have. And that would be that if I tell you that, for example, x is 5, that's a zero, or technically I should say a real zero, it means the following. It means that it is also an x-intercept. So the x-intercept is at 5. It means that x equals 5 is a solution. That means that if you use x equals 5, then f5 will solve or will give you a value of 0. And if x is 5 is a 0, then we also know that x minus 5 must be a factor of the original function. So all these are sort of based on the definition of what a zero means. And a little bit of this is just vocab. So x-intercept is another word for zero. I could call it a solution. The last word, and I guess I can just plug it in here, is that we can also call it a root. So zero, solution, root, and x-intercept all mean the same thing. Alright. Based on that, we can actually write polynomials if you know the degree and if you know what the zeros are. So if a negative 4 is a 0, then x plus 4 would be a factor, and x plus 2 would be a factor, and then x minus 3 would be a factor. So this has to be the function. Well, it doesn't have to be. That could be one of the functions that works. And the reason that I said that it doesn't have to be, and I should have given myself a little more room. So let's see if I can redo this a little bit. So let's bring it over. So keep in mind that those are all factors. I could plug whatever I want in front here. So I could put a negative 2 here, or a negative 2 over 7, and a whole bunch of other numbers. So there are an infinite number of polynomials that have a degree 3 and that have these zeros. Okay. And the last part I guess that I need to talk about is why is the degree of 3 important? Well, if the degree is 3, then the most that you can have is 3 solutions. So degree 3 means you can have at most 3. So we have 1, 2, 3. So this one works. If this was a 4th degree, then there would be like another factor here. And it would be an x minus an unknown. And so that makes this pretty much impossible to answer if it was a 4th degree. Another concept tied to zeros then is the multiplicity of zeros. And the multiplicity of zeros just means the following. And it's not a real math definition, but it is how often does the zero occur? That's what multiplicity is asking you. So, here's an example. X plus 4 cubed, x minus 2 to the 4th. Find all zeros. Well, so the zeros would be this. Either x to the, sorry, wrong power there. X plus 4 cubed needs to be 0, which happens when x is equal to the negative 4. But this cubed means that it counts as 3 zeros because it occurs 3 times. So the multiplicity here would be 3. And if I look at x minus 2 to the 4th equals 0, then x equals 2 is the 0, but because of that, this one counts as 4 zeros. So that means that the multiplicity is 4. And you're wondering probably, why does that matter? Well, the multiplicity tells you something about what happens on the graph. Does it cross or does it touch? So it says here, if r is a zero of even multiplicity, well, let's look at a function that has an even multiplicity for its zeros, like y equals x squared. What happens to y equals x squared? Well, if you were to graph that, y equals x squared touches. So an even multiplicity is always going to touch. Now, does it mean it always has to touch at 0, 0? Well, no, because you could certainly take this and we could slide this over and move it over here. Does it still touch? Yes. Well, this equation might be, but that would be an x minus something, right? So if that's 2, it would be x minus 2 squared, and that would be the right graph. So even multiplicities touch. An odd multiplicity, for example, y equals x cubed, that y equals x cubed crosses. So an odd multiplicity, so the 0 crosses the x-axis. That means that the graph always goes from a negative to a positive, or clearly we could also cross this way. So that could also happen. Okay, so odd multiplicities, they cross, and even multiplicities your graph touches. And based on those couple of things, you can now sketch polynomials if they're given to you in the right form. So this polynomial here, I can sketch that for you. Okay, and it starts basically by finding intercept. So ignore the negative for a moment. So x cubed equals 0 when x is 0, and the multiplicity here, multiplicity is 3. So if that's an odd multiplicity, at 0 it's going to cross. This function crosses at 0. X minus 3 squared is 0 when x equals 3. The multiplicity here is 2, which is even, so it's going to touch. And then here, x plus 2 squared, or I'm sorry, x plus 2 is 0. Well, that occurs when x is a negative 2. And that's an exponent of 1, so the multiplicity is only 1. And then that means that it's going to cross. Okay. So that gives me a pretty good idea of what's going to happen here with this graph. Sorry, I was trying to see how much room I had below it. So not a lot, so we'll do it on the side. So I'm going to mark the zeros, and then we'll see what happens. So I get a 0 at 3. I get a 0, I'm sorry, I get a 0 at 0, I get a 0 at 3, and I get a 0 at a negative 2. Okay, so now I have a couple of options in terms of what can happen here. So the graph can start like way up here, and then if it starts way up there and it approaches this negative 2, so it says that it crosses, so it does this. And then let's see, at 0, that's the next one, at 0 it's going to cross again, so it does this, and then it goes up for a little bit, and then at positive 3 this thing has to touch, so it does this. So this is a possible function. This is a possible graph for this function. Now the only other thing that I haven't really spoken about, but that we can probably figure out is, what does this negative do? Well, that negative means that this function should be negative when we have very large values of x. And right now you can see that this is going the wrong way. So the last part of this, and that's end behavior, and we'll deal with that in a little bit, but we need a little more information if we wanted to sketch it. But you already know some of this. So for example, the reason I'm telling you that you already know this is that if you look at a negative x squared, for example, negative x squared, well, that graph looks like this. The negative makes it go down on the right. How about a negative x cubed? Well, negative x cubed looks like this. The negative makes it go down on the right. So that's what should have happened here. So that graph was a good guess, but because of the fact that it said a negative, I think it needs to look like this. So it touches here, so that means it does this. Then it's going to cross at 0, and then it's going to come back up a little bit, and then it's going to cross again here. So the graph probably looks more like this. Now, why do we call this a sketch? Well, You can probably figure that out yourself, but see if we can name it explicitly. I have no idea how high these humps or how low these humps are in. Well, this one I do, but I don't know how high or how low this goes. And that's okay. This is a pretty good sketch for that function. Based on that graph, we can also then talk about turning points. So turning points are where the graph goes from increasing to decreasing, and decreasing to increasing, and then back again. So those are called turning points, and I call them humps. And it's probably pretty clear to see why I call them humps. If you know the degree of the function, then you know the maximum number of humps. So for example, if I have a function and it says it's like an x to the third plus 2x squared minus x plus 7, then I know that the number of turning points, or the number of humps, here is going to be 2. It's always one less than the degree. And so if you have younger brothers or sisters and you still have to listen to Barney every now and then, there's a song about Sally the camel, and Sally the camel always loses one hump. So that's sort of what I remember here. So this represents a camel. I only see 1, 2, 3 humps. So this one could have been an x to the 4th. So this could be an x to the 4th. It could be more. It could definitely has to be an x to the 4th. Okay? And we'll see that a little bit more in some pictures here. So let's see what we have here. Which of those graphs can be the graph of a polynomial function, and then list the zeros and state the degree that the polynomial can have. For those that are not, say why not. Okay, so A, is that a polynomial function? Well, that's smooth and continuous. There's a problem right there. So because of this here, we can say this is not a polynomial. Just keep in mind polynomials have to be smooth, which it is, and continuous. And if it's not a polynomial, you don't have to worry about the degree. This one is smooth and continuous. So if we count the number of humps, one here and one there, so there are 2 humps, then this would be an x to the 3rd, most likely. So this is a 3rd degree function. This one over here, smooth, well, it's not smooth here. So that's a corner. I have a different word for that, but we can't have sharp turns like this. So that is not a polynomial. Okay, and then the last one, smooth and continuous, we have 1, 2, 3 humps. So this could be an x to the 4th. So that would be a 4th degree function. Okay. So let's look at end behavior. It says here that for large values of x, and an x to the n, blah, 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 blah. So let's look at that a little bit more like this. So what, for example, if this was a 4x to the 6th plus a 3x to the 5th minus a 10x to the 3rd, etc., etc., etc. So end behavior is going to deal with what happens when x is really large, either positive or negative. So I'm interested in, for example, what happens when x is like a really large number. So what happens here? Well, if you look at this function here, you would do 4 times a 1,000 to the 6th. Now, a 1,000 to the 6th means that you have 1,000 times 1,000 times 1,000 times another 1,000, so that's only 4, right? So 1, 2, 3, 4, that's my 5th, and here's my 6th, and then we need to fill in the same thing over here, and then you keep doing this and this. But what happens is that these multiplications end up being so large that all the other stuff really doesn't matter. So what happens here is that this function, this f of 1,000 for a 4x to the 6th plus a 3x to the 5th, etc., it ends up acting just like if it was a 4x to the 6th only. You can ignore the other parts. And we know what a 4x to the 6th does, because that's a power function. A 4x to the 6th would have a dot initially here and here. So it goes through 0, 0, and then it goes through 1, 1, but then the 4 makes it go through 4. So let's see, if that's 1, that's 2, that's 3, that's 4. But what happens after that is that this thing goes up super fast. Sorry, I missed the first thing. So what happens here is that the end behavior is that when x is really large, so when x goes to infinity, the function goes to infinity. And on this side, the same thing. When x is really negative and large, then the function still goes to positive infinity because the negatives are going to keep canceling each other out. It's an even number of negatives here, and that means it still goes up. So the end behavior is just determined based on the largest degree, and then if it's an even, on both sides it will go up. If that were an odd, if that was a 4x to the 5th, for example, and then a whole bunch of other stuff. So if the original function had been, so how can I do this sort of quickly? So we'll do it this way. So if that was a 5, and that was a 4, and then that was a 3, etc. So then the function in its end behavior would act like a 4x to the 5th. And 4x to the 5th looks a little like this. So then we would say, well, when x is really large and positive, then the function is going to go to positive infinity. When x is really large and negative, the function goes to negative infinity. And that would be end behavior. Okay, we'll do this a little bit more formal now. So the end behavior, for example, we have a function and we know that n is larger than or equal to 2. Well, let's just make it an x squared. That works. And then we want the a to be positive. So this number a has to be positive, so let's make it a 2. So end behavior. So if this exponent is even and the a is positive, then the end behavior is going to look like this. And you would write it this way. So for even degree, when x goes to infinity, the function goes to positive infinity. When x goes to negative infinity, then the function also goes to positive infinity. What happens if you have an even degree function, but now it's a negative coefficient out here? So what if that was a negative 2x squared? I forgot to sort of graph this. So the graph would look like this. Well, then the graph would look like this. So what happens here is that when x goes to infinity, the function goes to negative infinity, but the same thing happens on the other side. It still goes to negative infinity. So even degree, an even degree function has what I would call the same end behavior on for x going to positive infinity or x going to negative infinity. So let's look at what happens with an odd function. So formally, let's pick one. So here we'll make it a positive 2x cubed. That's weird. And a positive 2x cubed would look like this a little bit. Okay, and you can already see what's happening here. For this one, when x goes to a positive infinity, the function goes up. Okay, so when everything's positive, the function goes up. When x is negative, the function goes towards a negative infinity. Because of this over here, because the negative doesn't cancel itself out. If I change the leading coefficient, so now I have a negative 2x cubed, then when x goes to positive infinity, so on the right side, the function actually goes down. And that means that on the left side, oh, I forgot the negative there, so when x goes to a negative infinity, then the function will actually be at a positive infinity. So odd degree, the O for odd corresponds with opposite end behavior. Okay, let's see if we can use that to sort of figure out what in the world is going on over here. So which of the graphs in figure 18 could be the graph of, so this is an x to the 4th. So an x to the 4th, that's an even degree, right? So we have the same end behavior. In this case, since it's a 1, which is a positive, the end behavior here is the same, and it needs to go up. So this one is done. That one works, and that one works. Okay, what else do we know? Well, it's an x to the 4th, so Sally loses a hump, so it could have at most 3 humps. Okay, an x to the 4th, 4th degree. So I'm looking for 3 humps. 3. 1, 2, 3, 4, 5. It cannot be this one. This had to be an x to the 6th at least, or a 7 or an 8. Depends on the multiplicity of some things, which we'll deal with in another section. Okay, so this one 1, 2, 3. This one 1, 2, 3. So right now it looks like I'm stuck between A and B, and I'd have to like plug in a whole bunch of numbers. Well, let's just check one number. What happens when you plug in a 0? When you plug in a 0 for x, you get an x-intercept. So 0, 0, 0, 0. So at 0 I should be at a negative 6. So this one crosses at a negative, that one at a positive. So there's the function. That's the only one that can work. So based on the things that you learned previously and then what we learned today, you can actually match the graph with the picture. Alright, so here's a summary of kind of things that we've talked about. The degree of the polynomial is the largest exponent. The maximum number of turning points is n minus 1, so at 5th degree you could have 4. Even multiplicities, touch, odd, cross the x-axis. Between zeros you have to either be above or below, and I'm going to go over that, but hopefully that makes sense. And then end behavior says, well, if you want to know what happens when x is really large, either negative or positive, just look at only at the first term. So based on all this, we should now be able to analyze that function. Now I think that might, no, that's not the same one we did earlier, right? Let's check. Where did I do my sketch? I actually sketched a more difficult one. Okay, so let's do one more of these. So what happens here? Sketch the following function, describe the end behavior. So if you want to sketch the function, you need to find your zeros. So there's a 0 here at x squared. Well, actually there are 2 zeros, so that's 0. And the multiplicity here is even. So that means, well, it's 2, which is even, so it touches. X plus 3 could be 0. Well, that would be when x is a negative 3. The multiplicity here is odd. It means that it crosses. And then the last one, x subtract 3 is 0. That happens when x is 3, which is also has an odd multiplicity, so it crosses again. Okay, let's look at end behavior. Now, describe the end behavior. So in this case, I actually want a formal description. And the formal description always looks like, well, what happens when x goes to infinity? What does the function do? And what happens when x goes to a negative infinity? What does the function do? So for formal descriptions, you have to do this. And in this case, I did want a formal. So let's check. So what's the overall degree here? Well, that's 2, and that's a 1, and that's a 1. So this actually acts like it was an x to the 4th. And an x to the 4th is an even, so we have the same end behavior. So now it just depends on the leading coefficient, and the leading coefficient is going to be negative because it is negative. Because all this stuff multiplies it out, and then you say take the negative. So the negative makes that this one is going to go down on the positive side, and that means it also goes down over here. So there's a formal description of the end behavior, and then that leads me enough information to sort of graph this. So this particular function has a couple of zeros. So a 0 here, it touches, and then at a negative 3 it has a 0, make it 4, and then 1, 2, 3, 4, and a positive 3 it has a 0. And then what does it do? On this side, it goes down. So I usually start on that side. It crosses here. It touches there. And it crosses there. So this is a reasonable sketch for this particular polynomial function. Okay, thanks.